this lecturer program. We have our Dr. Jasmin Grosinger from the Graz University of Technology, Austria, to deliver a talk on RF design for ultra-low power wireless communication system. So, she is an associate professor at the Graz University of Technology in Austria and also a visiting associate professor at the Tokyo University in Sendai, Japan. She earned her MSc from the Vienna University of Technology and worked as a project assistant with the Institute of Telecommunications. She later became a laboratory associate with Disney Research in Pittsburgh, USA. In 2012, she received her PhD from the Vienna University of Technology. Since 2013, she has researched ultra-low power microwave components and systems at Graz University of Technology's Institute of Microwave and Photonic Engineering. She has also been a guest professor at Frederick Alexander University, Erlangen, Nuremberg Institute of Electronics Engineering. She is an IEEE senior member and her research has resulted in more than 80 peer-reviewed publications and one US patent. She is actively involved in the technical program and steering committees of various microwave-related conferences and is an associate editor of the IEEE Microwave and Wireless Technology Letters. She is also a member of the IEEE MTTS, which is known as Microwave Theory and Technology Society, and was elected as a distinguished microwave lecturer. In 2022, Jasmin served as the MTTS EdCom secretary. Since 2023, she has served as an elected voting member of the IEEE MTTS EdCom, chairing the meetings and symposia committee since 2024. Welcome here in our very greenish triple IT DMJ campus. And I request to please begin with your talk.
Thank you so much. Thank you. Thank you for having me. I'm super happy to be here. And also thank you so much for hosting me. The campus is very beautiful. Before I start with the talk and with the technical part of the talk, I thought I'll give you a bit of background also of Graz and the Graz University of Technology. So here what you can see, this is the major site of the city. It's in the middle of the city, a recreational area. It's the Grazer Uhrturm. We speak German there. And it gives you a really good view of the city. And as you can see in the picture, it's already winter there. And the city has a size of 300,000 people. And I have to admit, this is already the second biggest city in Austria. So not comparable to the cities you are having here, of course. Our capital, Vienna, which is well known due to Mozart and the opera and all this other cultural background, there we have 2 million people, and that is our biggest city. And I really invite you to visit Austria once, Vienna, and of course, Graz. Graz is more of a university city. So the university, as you can see it here, the main building was founded in 1811, back when we had still the monarchy, by the Archduke John of Austria. And it made then its advance through history, as you can see, until 2004, where the universities reached more autonomy, which just means we have to take care of raising funds and money ourselves. And the government is funding us a bit less. But in the end, we have 7 faculties. It's just a technical university and around 100 institutes. And I'm with the faculty of electrical engineering and information technology. And I have a movie for you. And hopefully you can see it well and you can hear it well. So this is the fact. Oh, sorry. This is the faculty I'm based at. Now that the echo is gone. And I'm affiliated to the Institute of Microwave and Photonic Engineering. And there you can see a few photos of the equipment that we are offering. We have two anechoic chambers. Here you can see the chamber for the low frequency range. We have a smaller chamber for higher frequencies. We have wafer probers to really also then measure integrated circuits if necessary. And there you can see the head of the institute, Professor Wolfgang Bösch. He's explaining to Jose. No, actually, it's the other way around. Jose explains the wireless power transfer setup that he built up in my group to Wolfgang. Also here you can see Darshan Shetty. He also made his PhD within my group together with Infineon Technologies. And he was working on a passive wake-up receiver integrated in CMOS. And he's now still in Austria working for Infineon again. As you hear, we have a lot of companies in the area, in particular semiconductor industry, which is very nice, of course, for doing this research. We have Infineon Technologies, NXP Semiconductor, Renesas, Austria Microsystems. So it's a very good place to be if you're working in this field. I'm working in this field since a few years already and did also my postdoctoral degree in this field. And the motivation why we are working on radio frequency design for sustainability is the following. If you take a look at this picture, you'll see just a schematic of how the internet will look like, the Internet of Things, where we speak about connectivity for everything. The vision of the Internet of Things is that we connect everyday devices in our life, in our professional life, wirelessly to the internet. And for this wireless connection, we will need transceivers. But these transceivers are very power hungry. We will need batteries to power these transceivers up. And if we want to make this vision really happen so that everything is connected wirelessly, one estimate of wireless nodes that we will need to make this vision happen is 10 to the power
विषय से सिर्फ उन्हीं को सॉल्व करना है कि वो जो डेरिवेशन
जो आप कर सकते हो सब कर दो।
डेरिवेशन
हाँ हाँ।
It's hard to focus on the online audience when you have an audience here, no? Okay, thank you. So in this talk, I want to show you some solutions that we realized in the recent years, for example, together with Infineon Technologies. And one solution for the IoT is this one. It's a battery-less sensor device that we power up using HF RFID technologies, radio frequencies, and we don't thus need any batteries here. And also, it's very densely integrated, where we use, in this case, CMOS technology as well as wafer level packaging technologies to even integrate the antenna as part of the device. When I speak about the RFID technology, you might know it well. Its acronym is radio frequency identification. You might know it well when you use your phone for contactless payment. It's the same technology at high frequencies. This is the technology in the phone. At ultra high frequency, this is usually used for logistics applications, which provides longer communication ranges. But here we provide to the devices the power wirelessly by the reader device, by the interrogator, and thus don't need any battery. And for communication, we use usually something called load modulation or backscatter modulation, which is very power efficient. And so you can you can really operate without a battery. The RFID technologies, in particular, the technology, the interface that you use for payment, so HF RFID, was invented actually in the Graz region by colleagues at NXP. Semiconductors. And of course, we're super happy about this. The technology operates in the near field, so the distances that we usually can reach is about 10 centimeter, as you know, from payment. Or there is one standard, it's called vicinity standard, where we can reach communication distances of up to 1 meter. But this is also more used in logistics and not for entry or payment. How the technology works is the following. You have here the interrogator, the reader device, which is essentially a capacitance and an inductance established by this coil that creates a magnetic resonance at 13.56 megahertz. And the counterpart is the sensor device itself, the communication device. You can see here the CMOS chip in a package connected with the coil. Also here, the chip and the coil constitute a capacitance and an inductance, and you realize by choosing them wisely a magnetic resonance at 13.56 megahertz. And so if you bring these devices together, they're able to communicate. In the end, the reader provides power by the magnetic field that this sensor tag, this sensor transponder can then harvest to power up its circuitry and start communication of its sensor data. So this is operating at 13.56 megahertz, very low frequency. There is also standardized RFID technology, as I said, more used in logistics at ultra high frequencies. This is the range between 860 to 960 megahertz. And there you can read ranges up to 10 meter. And the reason for this is we operate in the far field. So we use classical antennas for establishing communication between the interrogator and such a transponder device, such a sensor device here. Here's the chip. Here is the antenna connected, usually a dipole antenna. And so you rely on electromagnetic wave propagation, reception and transmission in the far field, thus the longer, the wider read range. If you take a look now at these setups, at these devices, for example, this antenna here, this dipole, which, as you know, a half-wave dipole usually has a length of half the wavelengths at 1 gigahertz. This would be a wavelength of 30 centimeter, 15 centimeter is half a wavelength. So for this device to be actually very good, it should be 15 centimeter in length. So this is huge. So the antenna part of these devices is huge. Also for payment, these coils that we use, they typically have a size of 8 times 4 centimeter at HF for the near field. And also this is huge. So to really miniaturize the devices and maybe make them even more cost effective, use less rare material to be more sustainable on an environmental level, to miniaturize these devices, you have then to miniaturize the antennas. And so, however, what you always have to deal with is as soon as you stick to the same operating frequency and you just miniaturize the antennas, you will have a bad antenna at hand, which relates then to a read range reduction. And so with these miniaturized devices, you might then be able only to serve a few applications and not all applications that you're aiming for because of this reduced read range. And this is what we've looked at, dealt with, and actually solved. That's good to know. But it's not only us who worked in this field. There's actually already some classes outside, some miniaturization classes for these devices. Here you would have your classical conventional size payment card. 8 times 4 centimeter. Here is the CMOS chip, the coil connected to it. Here is another conventional sized UHF RFID device where you see it's kind of a dipole antenna with a bit of meandering and top loading. It's reduced in size a bit further. One option now to reduce the sizes of these devices considerably is to embed the coils, to just use coils and embed these coils in the package of the device. And then you get down to an area of the devices of about 2 square millimeter. And here you can see some solutions. This is one solution. I will show you in a few more details later, a coil on systems tag. And here we have the coil as well as the communication and sensor chip, everything included in the package, everything without battery, of course. And then there is another device. It's called coil on module, and it's an Infineon product. And you can see here is the chip, and here is the coil attached to the chip. And it's actually for payment cards. This is the back side of the device. And here you can see the top view. And this top view is actually the same as you can see when you look at your credit cards. It's the contact for contact-based payment. And on the other side, you just see then the coil for contact-less payment. So for using NFC for payment. However, the size of this coil is very small. And so the read range that we can serve with this standalone device is about 1 centimeter. And so usually, as I mentioned before, it should be 10 centimeter for this one specific standard. And our customers are used to 10 centimeter. So a standalone solution is actually not an option. But there is the option to use this device plus a so-called booster antenna. And I will show you a video later how this works actually, to extend the read range then again to the 10 centimeter the users are used to. Of course, opening up way more applications as the payment use case. If you want to reduce the size of the devices now even further, you could do this. You could just bring your coils on chip. Here are some solutions together with Infineon technologies. The area size is as little as 1 square millimeter. And here you can see actually a solution that operates at both frequencies, at 13.56 megahertz and at 868 megahertz. And this little guy is also a quite interesting solution. There we don't use magnetic resonance coupling or electromagnetic wave propagation as a means to communicate with the reader. We actually use capacitive coupling. That is why we call this tag OC free tag, on-chip capacitive coupled tag. But for these realizations here, the read range is very, very small, just a few millimeter. And it's essentially limiting, of course, then the applications very much that we can serve with these devices. However, we played around again with booster antenna technology, and then we're able again to extend the read range favorably, which is a very good thing. The research on miniaturized tags actually started back in the 2000s when RFID arose, and then suddenly we tried to do some other things with RFID. And one idea by the French Telecom was then to include the coil on chip. However, they were never able to show in their first prototype, as you can see it here, successful read range measurements. It took until 2007 until a company, the Broadcom Corporation in California, showed a first successful demonstration and wireless test of a coil-on-chip tag, as you can see it here, at 900 megahertz. And then it took another 4 years until at the Nagoya University, some researchers were finally able to show a successful test at 13.56 megahertz. And if you think of the corresponding wavelengths of these two frequencies, then you can imagine how hard it is for a 22 meter wavelength, 13.56 megahertz frequency to realize a really working prototype with a coil on chip. It's with an area of maybe a few square millimeter. Back then, of course, this was a great success. And today I want to show you also our contribution to this journey. And I will give you a few more insights on this coil-on system tag here, which is a full-fledged sensor tag, and this on-chip capacitive coupled tag, because it's also a really nice solution and quite innovative. Speaking about applications, there, of course, if we just have this miniaturized or this reduced read range of this 1 centimeter, then we can serve applications like this, point of care testing. You would have your sensor device here. This is actually where we had our sensor device. It was a biomedical application. The sensor device with the sensor interface was here. We put then some liquid with magnetically marked biomolecules on top to detect then these biomolecules. And the reader device you can see here, and it's powering up using magnetic resonance, this little guy here, to really read out the sensor data and also perform the sensing signal processing that you need to do really on device. Here you can see this 1 centimeter is fairly reasonable. But as I said, for payment, 1 centimeter wouldn't be enough. So we use booster antenna technology also for the coil-on module. And here you can see such a setup. It's fairly complicated to understand, but I have a video which helps you then to understand the technology a bit better. So think of it, you have your coil-on module with the coil in the package. Then you have also in the credit card this booster antenna, which consists of this small coupling coil that you align then with the coil-on module. So you have between the coil-on module and this coupling coil inductive link with which you then provide power. And then you have this little coupling coil galvanically connected to this pickup coil. It has, again, the size of 8 times 4 centimeter, so that you would manage a 10 centimeter read range. And this pickup coil then helps you to really draw more of the magnetic field and induce more voltage and currents and to power up the device. And the technology was actually invented because if you take a look at classical cards where you would have the chip and the coil galvanically connected, the most expensive part of these classical cards is this galvanic connection between the chip and the coil. So by using coil-on modules and booster antennas, There you don't have any galvanic connection between the chip product and the coil that you use embed in your credit card. And by this, it's cheaper and economically more sustainable. Here is now the video, and I'll try to explain it. You can see here the payment chip with the coil-on module. This is the top side with the contacts, as you can see. For payment, of course, security is vital because no one wants to have a breach when it comes to payment. Here you have the payment terminal that provides then the magnetic field that couples then into this booster antenna. And through the booster antenna, it also couples to the coil-on module. And by this, you're then able to establish this 10 centimeter read range that you're aiming for in payment. But to be honest, I read a newspaper article just 1 month ago provided by Infineon. They just came out with a standalone product without booster antenna technology, an optimized coil-on module with 4 centimeter read range. And of course, they're promoting this device very much, in particular because of its sustainability, because you don't need the booster antenna anymore. That will need metal material, and metal is kind of not sustainable. It's not biodegradable yet. So this is a very big step forward using this standalone device for payment then. And you can check your credit cards if you have it in there. Usually it's just written if it's a coil-on module or not. Now, yeah, that was actually the high-level overview. Now you have a good idea of what happened in the field. Now I just want to give you a few more technical details, but also still on a higher level so that it's still entertaining for all of you. This is now this coil-on system tag that I mentioned, this full-fledged batteryless sensor tag, where we saw the picture at one of the first slides. And what you see here is just a computer tomography of the device. And you see now not the packaging material anymore, but you see here this impedance sensor here, and then vertical interconnects, where we use the redistribution layer of the packaging technology to realize these interconnects, and also then the coil later on. And then the sensor interface, of course, connects the sensor to this red CMOS biochip to perform then the detection of these magnetically marked biomolecules. And then you have, of course, attached for communication this HF RFID chip as we use it for payment. And our part was now in this project where we had a lot of partners, of course, also people who are knowledgeable in sensor technology and biomedical applications. Our part was now to establish communication, power transfer, and data transfer. And so the design of this coil was one thing that we had to do. And how you do this, I just want to show you in a few minutes. Thinking of the system again, you would have an interrogator, which we call very often reader. And then you have your sensor device, which here on this slide I call tag transponder. If you operate in the near field, so coupling between two coils, which is denoted here by this coupling coefficient K, then the power or every voltage that you have available here at the chip input or at the reader input varies a lot with, of course, the distance of the coils and the alignment of the coils, which is then reflected by a range of coupling coefficients that we have to serve for a certain application. And so the first look that we take is for such a design to take a look at the system level using equivalent circuits because you're faster in calculating and solving these equivalent circuits. And make sure you have enough voltage available at the tag chip input. Here you can see the reader, as I said, and the tag on the right side. So, and the reader with the reader chip, a matching network, is then connected to the reader coil. And for magnetic resonant coupling, of course, the chip and the coil, they need to be create with their capacitance and inductance a resonance at 13.56 megahertz. And you have to make sure of this. And also on the other side, where you have the tag coil, represented by the same equivalent circuit as the reader, then connected to the tag chip that you want to power up. So what's essential, of course, also on the chip side is to create then this resonance at 13.56 megahertz by using the capacitance and the inductance. So you have to take a look at the chip capacitance that you usually know from the data sheet. And now, because you know where you want to be resonant at 13.56 megahertz, you can calculate what is the inductance that I need for the coil to make resonance happen. And here we've just followed this little equation, really not taking into account these other components here, just taking a look at the product of the coil inductance and the chip capacitance will give you then the resonance that you're aiming for. And as we have resonance frequency and the chip capacitance available, we just calculate what is the inductance that we need with respect to a varying coupling coefficient, of course, to serve the application. And this is what we did. At a chip product with a capacitance of 56 picofarad. We then calculated for our application, we would need a coil inductance with 2.33 microhenry. It's a small coil, it's a small inductance. We then went back into a full wave electromagnetic field simulator, simulated, of course, also the packaging material where we had an epsilon R of 4.1, all the other metals that would affect our coil design, and then designed the coil to create this inductance. And the end effect, the end result you can see here with 19 bindings. And you can also see here some extra pads where if we would not have enough inductance with our prototype, we would be able to add here a bit to make resonance happen. So we realized this, and then of course we had to do our wireless measurements, because without wireless measurements, it's not a demonstration. So the size, as you can see, is as little as 6 times 4 millimeter, very small. Here's the reader device coming with a coaxial cable, some matching to the reader coil. And this is the setup, as you can see, and we were able to reach a read range of 1 centimeter, serving the application that we intended for point of care testing. But as I said, we played around a bit with booster antenna technology. And here you can see one solution. You have here a coil on chip, so the coil directly on chip. It's very small, and the student thought it might be even possible to embed this little guy into the human body and mimicking some tissue, human tissue with water. He figured, okay, then we can use a booster antenna with this coupling coil here and the bigger pickup coil that isn't just a plaster. And you read out then the sensor data, which in this case was temperature, an on-chip temperature sensor. So as you can see, although this little realization, the standalone chip would not be able to serve this application, with these booster antenna technologies, you are. This is quite interesting. Now, for the rest of the few minutes that I have available, I just want to show you this other realization that I find particularly nice too. It's this OC3 tag, on-chip capacitive coupling. So we don't use here magnetic resonance. We use just capacitive coupling where we need electrodes. And you can see the realizations, the prototypes here in comparison to this 1 cent euro coin. And the area of this prototype is 1 square millimeter. So it's very small. And we just used electrodes on the top and the bottom of this chip to then establish a connection with the two other electrodes at the reader. And one electrode is just the top metal layer of the silicon chip, an easy realization. And the other electrode is just the chip substrate connected to ground. And by this, we just have electrodes at the tag that we can read out or power up the chip then with some other electrodes from the reader. And an advantage here is this is, of course, because we don't work with resonance, we are frequency independent. So in this realization, we serve both frequencies because we had available a dual band RF front end operating at both frequencies, 13.56 and 868 megahertz. And so we could show the frequency independent operation. And another benefit of capacitive coupling is not affected by metals next to it. While if you would have here coils and you would have metal next to it, you would have the countermagnetic field that reduces then the original magnetic field. And this would be an impairment again. But yeah, the equivalent circuit model, the system, the interrogator, the transponder looks in this case a bit different. We don't have coils anymore. So we just have on the chip side, these top electrodes and the bottom electrode. And on the reader side, we have another top electrode and another bottom electrode. And as you can see, these capacitances that are then created with top and bottom electrodes, you can calculate by using just the area, the distance, which would be the read range, the epsilon r, in this case, it would be 1, and then the permeability in vacuum. As easy as that. And then you just have a capacitive voltage divider where you just have to make sure you have here enough voltage, 2.8 volt, to power up and operate. And we did this. We realized the device and then have here the photo shows you the setup for doing these measurements, the wireless measurements. But I show you a schematic to make it a bit more clear. You have here again the reader with a bit of matching, and then the reader top electrode and the reader bottom electrode. And then you have here the tag with the tag top electrode and the bottom electrode, which was just a chip substrate connected to ground. And in between the bottom electrodes, we put a sheet of paper to really show full-fledged wireless tests. And then the distance, D1, is the communication range that you can reach. And the range that we reached at HF and UHF was very small, as expected. 100 micrometer for HF, 300 micrometer for UHF. So this is a very short communication distance. For some applications, definitely still okay. The student had the idea to tag Nespresso capsules and that the reader would then be in the Nespresso machine. And so when you enter the capsule, you close the machine, the reader reads out the tag ID and the machine prepares for you a delicious cup of coffee. That's one thing for this short range. But of course, again, we tried booster antenna technology. And here you can see some videos of the student showing possibilities to use booster antenna technology. This is Walter. He's now with Infineon. The HF reader with the HF coil. No, it's a huge coil, as you can see. And then the device with some booster antennas. And in this case, we needed 2 booster antennas to create the top electrode and the bottom electrode. And of course, alignment here is important. You would also have a coupling area. This is not a coupling coil yet. It's just an electrode, but it's the same thing. And then the pickup coil is the same coil as you use every time. And then you read out the electronic product code. And as you can see, the electronic product code was coffee. So I really suspect the student, he was into coffee a lot because he had all these coffee ideas, as you can see. This is now HF. But as we had this dual band front end, we could also realize a UHF realization. Because it's then just the same coupling area, the electrode, no, 1 square millimeter, and then a pickup antenna, in this case now a dipole, a dematched dipole. So this boost antenna technology is very versatile, as you can see. And now, of course, you have to align. We used some tape to show real capacitive coupling. And here you can see now the UHF patch antenna that we use. And you can see now how Walter reads out again the electronic product code again. Coffee, of course. And this is it from my side. I hope you had an interesting hour with me, and you see how we can really benefit also for a sustainable future and actually enable a sustainable future. All of us, is it electrical engineers or physicists, all of us can. And I'm of course excited to see your realizations maybe next year at the MapCon in Kochi. And with this, I have one last video for you by our sponsor, the Microwave Theory and Technology Society.
इतना बंदा खाली कर नहीं तो इधर डाल दे दूसरी इधर डाल दे बच्चे आपको मनोरंजन करे पता नहीं कौन से सवाल कर मेरे को भी नहीं मालूम कुछ दिन पर ड्राइंग करना शुरू कर दिया उन्होंने स्केल से मजा आता है हाँ ऐसे बहुत लगता है बच्चे बन भी जाते हैं
Thank you so much for your attention.
Now is open for question and answer.
Don't be shy.
Any sort of queries, concern, you may ask.
Yes, and of course, if you come up with some other questions, you can always contact me. You can see here my email address. So that is, of course, also an option.
A lot of work on the RFID tag, especially.
And in this talk, definitely, I will have also other work at UHF. But in this talk, it's specifically HF RFID.
So, in the UHF, like, what are the challenges not proceeding for that, for the higher frequency, gives the better range even?
The UHF is very concerning because of we have to deal with the wireless channel. And the wireless channel sometimes, as you know, if we have constructive, destructive signals, you will create these steep fades where you will have little power available in this specific part of the room if you are in a multipath environment. And so if the tag, such a battery-less device, is in such a deep hole, it will not power up. And this is very difficult. So metal environment is still a huge challenge. Metal environment is crazy, multipath environment. Physics is always there, and we have respect physics. We can just, come up with clever ideas like the booster antenna, how to exploit physics in another way. So EMI for the booster antenna shouldn't be a problem because in these chip products, usually there are these EDS diodes in there at the very beginning of the front end so that we don't have any troubles with electromagnetic interference. It could be. So I am not. I have a colleague, David Pomerenke. He works in the field of electromagnetic compatibility. The only issue that I know is in particular not at the transponder side, but more on the reader side. And there are a lot EMI issues. And so NXP once contacted me because they wanted to analyze, in particular, the interference at 433 megahertz of HF RFID readers. So the reader side there, you have troubles because you have a lot of components that you're dealing with. As I said, at the chip side, at the tag side, usually you have these ESD components and you don't have an active transmitter. So how to create any disturbance? Let me see. An online question. Wait. Oh, no, there is not.
You can read it.
Oh, someone has raised his hand.
Yeah, good afternoon. Am I audible?
Kapil sir, please ask the question. Kapil sir, please ask the question.
Yeah, am I audible?
Kapil sir, please ask the question.
Yeah, just I like thank you for a very nice presentation. I have two questions for you. First one is you are measuring body temperature using the RFID card. Are you using any external sensor or a chip that is like connected with a RFID tag? The first question.
Yes. Thank you so much. It's not the body temperature that we are measuring. It's just an on-chip temperature sensor. We are measuring the temperature of the chip. It was just a demonstrator. So it's not the body temperature and we don't use any extra sensor.
Okay, one more question is that have you tried any biological markers that you explode using the RFID tags?
So I was working once on using RFID tags on body, where, of course, I did some specific antenna design for on-body antennas. This was during my PhD work. But other than that, I'm not sure if I get your question correctly. So are you referring to like using any phantoms for design?
Sorry for the confusion. My question is with respect to the biological markers. For example, the glucose concentration or the uric acid on the blood or something like that can be explored using the RFID.
Definitely, there are some solutions. I'm not working in the field too much, like detecting biological markers. But there is a company, they are called RadioSense in Rome, in Italy, and they are doing a lot of solutions, and they are in close cooperation with Professor Gaetano Marocco. And they have a lot of UHF RFID sensor tags for biomedical applications, even showing some tags in body, so embedded in the body. So you might want to check out their website and their publications.
Really sorry, one more question I have that like most of the time RFIDs are used with the vehicular like tagging and other things. With a recent invention in LoRa module and other, what is the scope in the future?
So for RFID, an important factor is now bringing in sensing capabilities. So this is what the big thing in RFID is usually, or actually we try to fit in as much as possible operating batteryless. We have other solutions. It's not RFID, but it's same frequency, ISM 900 band, where we have a passive wake-up receiver that harvests radio frequency power, same as a UHF RFID tag, and has an RFDC converter to harvest this power. And the idea of this passive wake-up receiver is to power up then by request of any base station a full-fledged sensor node that is maintained by a battery. And the idea is that the IoT node should be in sleep mode as long as possible and only woken up by a dedicated RF signal, a signal pattern. And by this, you are able to spare battery life and then extend the battery lifetime from 2 to 10 years. This is not classical RFID, but it's a bit similar on the front end side of one particular part of the front end.
Thank you very much.
Thank you. Some companies now demand that to not use ferrite as a solution because it's a rare material and not sustainable. And an option is metamaterial surfaces. This is what we right now work on, with a postdoc. Thank you. The chai tea is really the best here.
So as far as the future scope, one is the chip side development in the RFID. Another is like application-wise the design, especially the coil. And if you talk about the HF frequency, like cutting the back, miniaturization is like a very important aspect as per the application, especially in the biomedical applications. So is there any solution that it can be like moving up for the higher frequency?
We have shown the solution at higher frequencies at 868 megahertz. Using a coil at 868 megahertz was the only way forward, because miniaturizing a dipole to an area of 1 square millimeter, you have no chance, no? At 868 megahertz. Yeah, so there is definitely an option.
So same like the designing topology or the equivalent circuit model will be working to the high frequency.
This is a bit different then. Let me think. Yeah, the coil design might be then the same. Now at UHF, we just use it as a bad receiver coil. Now it's not magnetic resonance anymore that we exploit. So it's just, I wouldn't know per se if it's just if you could use one-to-one the same equivalent circuit. I don't know it by heart. I've never thought about it.
Most of the design you have is the dipole antenna.
At tags, usually at UHF, you use dipoles because the tags are somewhere distributed in a room and you never know where they are. So you have dipole antennas with an omnidirectional radiation pattern. So, you have a chance to be in the read range of the reader. The conventional stuff for size reduction you can do is use a high permittivity substrate, meandering and top loading. But there you come, when it comes to 1 square millimeter in size, it's still not feasible to do this.
One more question is, what's the specific, what is the development of the challenges towards the reader side? This is the tab we discussed.
Yeah, the reader side, definitely EMI is a challenge. But I'm not working too much on the reader, I have to say. So one thing that we were working on was, because very often, one interesting thing is, you use magnetic resonant coupling for your NFC interface in the phone, but you also have mobile charging, wireless charging. It's the same technology, magnetic resonant couplings, but 100 kilohertz. So what we were working on was more on the system side, not reader side, more system side. What are the effects of these two coils embedded close to each other in the phone? And also with respect to powering up. So they're taking a look at the reader again. And what would be the disturbance coming from the wireless power transfer signal at 100 kilohertz at 13.56 megahertz then? And the other way around. Do we have any effect from NFC to WPT? It's interesting. You can open up these devices and you see two coils. The bigger one at the outer rim is the NFC coil, and the smaller one with a lot of windings, that's the key charging. Yeah. So this was something we were working on too.
Ma'am, I have one question. Like RFID tag, how it helps for wireless charging, like impedance matching and all.
So at UHF, impedance matching is very important. That is why I was not sure about, the question before, because impedance matching always comes first at UHF.
And of course, the chip, I think the chip offering the impedances will be different.
It's usually a complex
Yeah.
and capacitive. It has a very big negative capacitor, a real part, negative real part, because of the RF DC converter and the storage capacitor that you have to store the power.
So accordingly, the coil or the antenna will be designed more like inductive kind of.
Exactly. That is why you have these kind of T-match dipoles that I showed you before, so that you can reach other impedances for complex conjugate matching.
Ma'am, what you are using for the reader side, you're not working. Is there any pre-existing reader what you are using in your labs?
We usually use the existing ones. So, for every HF RFID test, we use our own phones. We have it. And you can use it to investigate the read range. You just have to specify which phone you're using in your paper, because otherwise it's not fair. No? And then there is an impinge reader at UHF. And impinge, they are very good. They are based, I believe, in the US. They have very good readers, and they allow you to take a look at the baseband signal. No, not really baseband, but already the amplitude and phase of the, let's call it passband signal, of the tag signal that you receive. So you can even do then localization, because you have the phase information. And we use it to use then at the tag, the UHF tag, the tag as an antenna, modulate then depending on the tag in the antenna environment. We modulate amplitude and phase of the tag signal additionally on top of the digital modulation with the identification number. And then we read it out using amplitude phase information. And this reader is very good for this. Now, as you can see, in Graz, RFID is very important because a lot of companies work in this field. And it is just natural that as a researcher that not everyone is working on RFID, but it's my specialization. And it's good to work with the companies, and have this already huge knowledge about the technology. So, but it's very specific to the Graz area. I have to admit.
My last question. Because I think how you're getting the information about the chip, like the impedance, capacitance, reactance, and all the parameters. Is it like the company providing this, or
No.
you are developing these chips into the institute itself?
So we develop ourselves in cooperation with companies, however. You need the process, for realization. You need the tape out. However, if you take any tag chip product, usually what we do is we just measure the input impedance ourselves. But this is not so easy because it's a small device and you have to be careful.
Yeah, one thing like some designer who designed this transceiver may have the information.
They don't have the RF information. Usually they are analog designers and they have not a good knowledge about RF, radio frequencies. And so it's difficult.
So extracting this information by...
It's better to measure it yourself. If you really need the information, measure it yourself.
Also, like somebody has been reported in the literature. Right.
Then you're lucky. Yeah. Then you're lucky. And then it's a chip that is used by everyone. Yeah, I I have now a student, a master student, working with NXP, and they use a chip now, a front end, that another student of mine developed for UHF RFID 868 megahertz. Energy harvesting is part of it, no? An RFDC converter. Now they're using it. They wanted to exploit this chip prototype at 2.45 gigahertz. And now the student is working on this, but they involved me a bit late. And so, but anyway, now I'm in, so it's good. We can work on this. It's, of course, if the front end is designed for 900, it is not that perfect at 2.45 gigahertz. It cannot be, no? But it's acceptable. We have some good results. We will publish them, although it was not intended for this frequency.
Luckily, it's working with that.
If there is no more questions, so we are proceeding for certificate for distributing. So I request and thank you, ma'am, for delivering us such a wonderful lecture. I hope everyone have received the fruitful knowledge about these RFID tags and coupling on chips, circuits. So in our lab, we also have a DNA fabrication machines. We also fabricate the structure and have a measurement facility up to 20 gigahertz. And we are hoping that in near future we can move up to the 40 gigahertz or 60 gigahertz measurement. As of now, in the recently concluded conference, which is MapCon in Hyderabad, they are offering the 40 gigahertz measurement facility without taking any charge to the institute which are located in the tier 2 and tier 3 cities, like this our institute.
Cool.
And earlier we were shortlisted for the Innovative Chamber up to 40 gigahertz measurement free of cost by JV Micronics. We hope in near future again we'll make sure that we can get up to the 40 gigahertz measurement. Now I request our honorable director sir to present the memento and certificate.
Thank you so much for staying on.
No, it's fine. I am a researcher, so I try to get some sort of knowledge from your talks. Yes. I have a head of department that also comes.
Sorry, I'm a little bit late.
Hello,
Hi.
how are you doing?
Yeah, fine. Please, it's yours.
Wow, thank you. It's beautiful. Wow.
This is a memory from Jabalpur, which is mainly for Sangmarmar.
Okay, so it's a marble city, so some stuff made of marble.
Oh, wow. That's it. Thank you so much.
Yeah.
Thank you.
So, yeah.
And you are collaborating with Darmstadt?
Oh yeah, I have been. I visited Vienna. I think your this technical university of Vienna, perhaps, right?
Yes, I studied there.
Yeah, during my postdoc career when I was in Israel. So I was taking this Tel Aviv Vienna flight, then moving to Paris, then Switzerland, Eurostar train, and all these things.
Cool. Yes.
And, and I've seen this. I think in Vienna. We visited some Jew in the city, then Mozart city.
Yeah, Salzburg.
Yeah, Salzburg. Yeah, so
Yes.
really, it's a beautiful country.
Yes. Yeah, really, if you happen to visit, all of you, please let me know. I'm happy to really show you around the facilities at the university.
Yes, sure.
Few more are there, sir.
Okay.
I request ma'am to present a memento to our director, sir.
Oh, I see.
See?
Thank you.
Wow, this is great.
I request director, sir, to present.
Head of department.
Thank you.
Yes.
Yeah. Thank you. Thanks.
Again, request to present.
Okay, na?
So thank you so much.
We have any group photo, no?
Yes, of course. Yes.
Please come all of to have a group photo.
These mementos are so beautiful. I will place them in my office.